Hey guys, I'd like to get started. Good afternoon. I've had a lot of emails from you forming groups for the assignment, so that's good. I think almost everybody now is in the group. If that's not the case, please try to do that and let us know so that we can prepare for the grading. The idea is that because it's a lot of group and we're actually going to write a report that's quite long and that's split among several people. That's why I would like to know who is in which group. So we're slowly nearing the end of the course. The topic of today is flow and perfusion. That is a topic that somehow dropped out during the Corona lectures because it had to all be reorganized a little bit, and for some reason it didn't get back last year. So now here it is again, which also means that for me it's a little bit rusty because I haven't given this class in a couple of years. So please, if I somehow forget some stuff, please forgive me beforehand. The recording on? Yeah, I think so. Yeah, it is. Yeah, I have to record it from there because somehow the webcam is not. My laptop is doing all the work. All right. A few questions because we are going to encounter these topics a little bit later on. So very quickly, if you know it, then just shoot me. Who can name some scattering theories for different particle sizes?
Or in the case when the particle is much smaller than the wavelength, that will be wave scattering. That will describe that scattering process.
Yep.
Mean theory for equal size.
Yep. Spherical scattering was geometric. So geometrical. When particle size is much bigger than the wave. Okay, we're going to talk today about.
Is that mean theory sort of describes all situations, including the ones where between radial and geometric.
Yeah, absolutely true. Provided that the particle is spherical, the mean theory is an exact solution for spheres. So as long as the particle is spherical, you can use that for all particle sizes. There is also, by the way, also a mean theory for cylinders, so that is also available. The difficulty with mean theory is that it is not very straightforward. You have to use a computer program to do that. Whereas for example, Rayleigh, it's a simple formula that you can believe in. You're absolutely right. So we'll be talking about blood flow, blood perfusion. So does anyone of you know what approximately the size of a red blood cell is? Yep. With units, please. Yeah, you.
Around 1.3 micrometers diameter.
Yeah, slightly small. Slightly bigger actually. It can be 3 to 4 micron. Okay, so if you then so thinking of the different theories, which one do you think is appropriate for visible light?
Well, because visible light, that is from 400 to 800 nanometers, so around 0.4 to 0.8 micrometers. So in the case when the wavelength is roughly equal to the size of the object you're measuring, so you have to use mean theory.
Yeah. So that's exactly that's also what. So I'm going to show you some calculations later on, and these are all done with mean theory for that. Okay, so if I have these, so let's say mean theory, also the other scattering theories, what do I have to know? What do I have to put into these theories in order to calculate scattering?
Yeah. So particle wavelength.
Exactly. Yeah. A few simple parameters, but if you know them, then let's see the computer does the rest. The theory does the rest. One of the outputs of these scattering theories is the phase function. Yeah.
Sorry, what was the third one?
Size of the particle, wavelength, and refractive index. Then actually refractive index is 2 because you need the refractive index of the particle and of the medium. Who knows what the phase function is? It was an output of these second theories, yes? Yeah, phase function describes how the light is redistributed into the different scattering angles. It is It's a normalized function by definition. So if you integrate the phase function over solid angles, so over the whole spherical domain, then the result is 1. So this can also that means you can also regard the phase function as a probability density function for scattering into certain. So working with the function itself is not always convenient. So we try to parameterize the phase function into numbers. And one of these numbers is the scattering anisotropy, symbol G. Remember what that was, what that number was, and what it implies when G is 1 or when G is 0.
G is 1 scatters in one direction.
Yeah. Yeah. We remember what direction? Exactly in the forward direction. So the phase function of the scattering anisotropy G is the average of the cosine of the scattering. So if all light scatters in the forward direction, then the scattering angle is 0. Cosine of 0 is 1, and then the average of all the light, the average is 1. So if G is 1, that implies that all the light simply retains its original direction. It scatters. If G is 0.
Equal amount of light is scattered in the forward direction as the back.
Yeah. Yeah. So the average of the cosine is 0, so that means that. Okay, then finally, we talked about modeling tissue using, for example, particles, and then one of the terms that came along was a discrete random medium. Remember what I meant with that? So discrete means that the scattering is done by discrete particles. So there are particles in the medium. Medium is of course a scattering substance. And random means that these particles, these discrete particles, are in principle placed randomly in that medium. So there is no predefined way of placing these particles. However, when these particles are yeah,
I think there's
an echo.
yeah. Like I get that.
Okay, maybe if I.
You're all falling down.
Yeah. Okay, that should fix it then. Okay. The particles are placed randomly, but should we stay?
Yeah.
Okay. Test again. I don't hear it anymore. You?
So, not right now.
Okay. We'll do that. Oh, this one.
That's
Okay, now it should be solved, I think.
Oh, yes.
Okay, so these particles could be placed randomly in the medium, but the only problem was that when the particles are, for example, hard spheres, then truly complete randomness is not possible because they cannot overlap in space, so they can at best touch but not overlap. So truly random, a discrete random medium is not. And that effect was described by the so-called pair correlation function. A couple of ways of describing that one. Do you remember what that was? I also want to briefly bring that up again because in the end of this talk today, it will also be make a short appearance. So these particles can take mostly random positions in the sample, but not entirely because they cannot overlap. So what the pair correlation does is quantify that effect by by making a histogram of the distances between particle pairs. So pair is from particle pairs, and you pick two particles in the medium and calculate the distance between them. You repeat that process for all the sets of particle pairs inside the medium, so you get a whole bunch of distances between these particles, and from that you make a histogram. So that means if you have a medium with only very few particles, with very dilute suspension, and you would make a plot of the histogram, and so you would plot here the distance between the particles divided by the diameter of the particles. So all the particles are identical, and you would plot here that function to the power. Then for all these pairs, you cannot find distances that are less than the particle diameter, because in that case they would overlap. So for distances less than R over D is 1, that would give you a zero result. Zero pair correlation. And if the distance gets larger than the diameter, then it is possible to find pairs there. So then this histogram gets some sort of value. And if you look at this case, it will look like this. So all the distances are then equally probable. To look like this for a very dilute space. The volume fraction is really small. The other extreme is when the volume fraction of the particles in the medium is very large. So in that case, just think of a bucket of marbles that you're trying to fill. At a certain point, you can't put any more marbles in there because simply you run out of positions where you can place the next marble. So what you will see there is that still a forbidden region here, so the particles still cannot overlap. So there will still be no distances between particle pairs for separation less than the diameter. But then at separations of the diameter, which two particles touching there, all of a sudden the probability shoots up very high. So if the volume fraction is high, there is a very high likelihood of these two particles being in contact. And if R is 2 times the diameter, the same thing goes. And if R is 3 times the diameter, same thing. Of course, it does not look this crazy. It looks more real. It looks more like this. Down a little bit here, and it goes up to here. You get the idea. So this is then for volume fraction really high. So that is the pair correlation function. It's a histogram. Describes the distances between these particles. Of course, that's all nice and good, but it simply describes something about the medium. So what is then the relevance of optics for that? Well, what we have in an optical measurement, we have a particle here, which is illuminated by some electric field coming in here. It scatters light into some other direction here. We place a detector here, we we determine an electric field here that has a certain amplitude and a certain phase. The phase is given by the distance from this particle to the detector. It's simply the geometrical key is 2 pi over lambda times the distance. If I have another particle, so here, which is illuminated with the same light, and the light of which is detected is seen by the same detector. That too has a phase that is given by distance to the detector. Because particles are in 2 different positions, so the phases will be different. So we'll find a phase difference on the detector between particle 1 and particle 2, and also between particle 1 and particle 3, and between particle 2 and particle 3, etc., etc. You get a whole bunch. You get a whole bunch of phase differences on the detector due to the different positions of these particles, due to the positions of these particles. That is why pair correlation function is important. And then the effect of that on the measured signal is described by the structure factor. Structure factor is the average of all the phase differences between all these particle pairs that are see that a little bit later. Good. So looking at the scale of which we're going to describe light propagation or light, the interaction of the light propagation is basically on two length scales, because we're going to look at flow and perfusion, movement of red blood cells inside tissue, so that's basically inside the tissue. But what we will be needing is also the individual scattering properties of individual red blood cells. We will also be a little bit of that presentation. So there's a couple of techniques that are currently available if you want to measure blood flow or if you want to visualize the perfusion in tissue. I've listed a couple here, and these are the three that are in the lines that will make it clear today. So I thought OCT, Johannes talked about a little bit, and we also briefly mentioned how you can use OCT to measure movement. That will be done. So first microscopy. Not first one. First the definitions of blood flow, of perfusion. What is it? So if you talk to a clinician, then they will use all these terms through each interchangeably. Blood flow, perfusion, that's all the same to them. Essentially, what we want to do is we want to quantify the blood supply to tissue. The blood carries the nutrients, so somehow we want to quantify how much blood is in the tissue, how reaches certain target sites. Since we're trying to approach to do a little bit more from a physics perspective, I've given definitions and units to these different quantities that basically all describe this one slide. We have blood flow, which is defined in a vessel. That is then measured in cubic meters per second. So that's really how fast a cubic meter of blood would move inside the vessel. Then we have perfusion, which is defined in tissue, which is given by volume of blood per volume tissue per second. So the speed at which certain volume of blood per volume tissue goes inside the tissue. And then the final is the blood flow velocity. It's also measured in vessels, and that has a familiar unit as expressed as of meters per second. And now, if you look at these units, and if you also puzzle around a little bit, you can find that quantitative blood velocity. So you can measure that. Then you're really a long way already in determining all these other things. Because if you measure the velocity, you know the vessel diameter, you can calculate blood flow. If you know the vessel diameter and you know the vessel density, then you know the volume of blood per volume tissue and you calculate perfusion. So the first, basically the first goal for all these measurements would be to first measure blood flow velocity, quantitatively, and then quantitatively. That's like this. Works. Can you maybe tell us what this slide? I think it's the most left one. Okay, yeah. So what this image shows is a microscopic image of the blood circulation under the tongue. What you can see here moving are red blood cells, so it is really simple imaging of the red blood cells. And then after that, a big chunk of software analyzes these images. So what you can do, for example, is track some of these red blood cells as they move along. From that you can calculate their velocity, if you know what that is. We can do image segmentation on these images to get boundaries of vessels and the image of the vessels. the volume of the process. So then in the end, what it becomes possible to measure the flow velocity, the blood flow velocity quantitatively in millimeters per second. So it's inside these red blood cells. One parameter that is also important to make is modeling here, for if you want to know how tissue is supplied with nutrients, that you also like to know the oxygen separation of the blood that goes there. Because even if blood goes there, if it carries no oxygen, then there is still no benefit to this. This form of microscopy is this particular form of microscopy is called side stream dark field flowmetry. That's kind of a name that is more invented for salespeople than anything else. But the idea is that so for the normal microscope you would have light illuminating from the back. You would measure the transillumination of tissue. Of course, that's not that easy to do in tissue. So here you have to measure first in reflection. And the way it is done here is that we have a small pistol-like device where light is emitted from the side. So you are like using diodes, that illuminate the tissue. And the light is reflected from the tissue and it's collected by a lens tube that is in the center of this house. Light can guide it to a CCD camera and that is what takes these images. So this for this instrument there's four fibers and 4 LEDs that you can see all the other details out there. Okay, so flow, in this case, so this particular device does the flow quantification by tracing the red blood cells through movements from frame to frame. And what you see here on the scale is more or less the range of velocities that can measure. Measures flows from flow velocities from 2 micrometers per second to most millimeters. The device uses green wavelengths because green has a high absorption. Blood has a high absorption in green part of the spectrum, so it means that if you have large contrasts, so the red blood cells themselves catch out the light and it causes contrast with the environment. So what do you get out of this device? It may sound a little bit like a sales pitch, but it's actually quite impressive. You get from these images and from the analysis of data, that more quality of the capillary beds, the size of the vessels, shapes, tortuosity, that's the way they are wrinkling, capillary density, volume fraction, and of course the red blood cell itself. And this device is used in the clinic actually quite a lot in the intensive care. You can use it for monitoring of intensive care patients, but it's really important to prevent septic shock, and you can clearly see that coming in changes in the perfusion in the microcirculation. So using this device as a really non-invasive instrument to regularly check if the perfusion is still okay, can help signal. Also it's used in surgery when sometimes the blood flow has to be interrupted during surgery and then started again. For the bigger vessel, that's usually not so much of a problem. That is connected again and the blood starts flowing. But sometimes the microcirculation, so the small vessels really downstream, they sometimes lag a response. So it's important to keep an eye on that as well. There's different diagnostic applications and also research and focus. You see them here. So this begs the question a little bit. Okay, is the problem solved then? We have this nice technique. It can measure a lot of things. It's used in clinical a lot. Are we done? Of course. The answer to that is no. So, clear advantages is that you can directly measure the cost, and that you can directly image the microcirculation, so that is a big plus. Disadvantages are the main one is that you can only measure very low flow velocities, 1 per less than 1 per millimeter per second. And the analysis is offline. This last part, of course, is something that is technological problems. And if you really want, and if you really have enough money, then you can solve that. But if you don't really, it feels fun. And also the low flows, if you can get faster cameras, that is also can also become better at the techniques. So the first disadvantage is they have present people that you don't. The second disadvantage has to do with the optics. Because of this green light, which gives huge contrast for blood versus environment, it also means green light does not penetrate as deeply into the tissue. So that means that we're most sensitive to only superficial capillaries. If you want to say something about vessels that lie deeper, then you either need to use light that penetrates deeper, so you have to go to a longer wavelength, but then your contrast with blood gets less, but then the signal goes away that so this is a real fundamental disadvantage that's related to the optics, to the light. So there are alternatives. They are grouped under the nominated laser speckle techniques. There's two of them. Advantages of these are that you can be sensitive to higher flow velocities. It's relatively simple, so the analysis can be done online, so the process moves. Another advantage is that you can go to a slightly higher wavelengths. You can probe a little bit deeper, which means that you get high sensitivity to flow in arteries and venules instead of just in the very superficial vessels. And then there are also disadvantages. One of them is that the assessment of morphology is more challenging. So that means that even though we can try to measure blood flow velocity quantitatively with these laser speckle techniques, then if we want to go to blood flow and perfusion, we need to know something about morphology, and that is not easily obtained from these techniques. We can separate easy techniques for that. And the disadvantages from the research perspective. It turns out the technique is pretty simple. It turns out to be hard to really make it blood flow velocity quantitative. Really be sure that the number that you get is really in millimeters per second correct. So there's the two techniques that do that. Are based on speckle laser and speckle contrast imaging. Speckle techniques. So first, the first question is what is speckle? Speckle. So to get you started, you can see that this is an old slide because this is really important. In which situation do you think that the cell phone reception is better? You have an antenna here and the cell phone over here. Fields in Macau, downtown Manhattan. Where do you think the reception is better and why? Yeah.
Since there are less obstructive elements within the field in Macau, we expect a more direct line of sight, therefore less light bouncing off in different direction, having a harder timing or having to reach you. So because there's a more clear line of sight in Macau, I would expect the signal to be better there.
Yeah, that's I think so. In the worst case of let's say Manhattan, you would have a lot of different light possible from the transmitter receiver. They will bounce off at buildings, they will bounce off at moving things like cars and trains, etc. And all these signals from that source to the detector, they will all interfere at the detector. Sometimes this will be constructive, sometimes it will be destructive, but it will also vary in time because if the cars or the trains move, then their contribution will change as well. So what you will get as a result is the signal, reception signal on your cell phone, and it fluctuates in time, and therefore it is sometimes stable. So this is of course obviously a problem in telecom. So what they try to do is then find all kinds of algorithms to recover the optimal signal. It is in the telecom industry, this effect is called Rayleigh fading. So specular optics is also is similar. It's analogous. It is a granular density pattern or random fluctuation in intensity that you can find, for example, if you shine a laser beam on a rough surface. You bring a laser pointer, so I can show you directly, but I think you're familiar with this effect. If you shine such a pointer on a rough surface, you see this granular pattern. And obviously the same thing happens there because the surface is rough. You get light bounce back from different positions on the rough surface, and sometimes it interferes constructively, sometimes it interferes destructively, and you get light areas in that. We also see it in images in OCT, for example. This is an OCT image of tooth, I think. We would zoom in here on this part between the crosshairs. So really zoom in, enlarge that. What you would see here is then a pixelated picture, of course, very strongly now, but also that these pixels are fluctuating in gray level in intensity. That's the same speckle light speckle fluctuation of the random fluctuation of it. Put that a little bit more formally. So this is what would happen for the case of the laser pointer, for example. We have a laser pointer in the surface, an observation point, or eye. If you look at this pattern, we'll see different contributions of electric field at the observation point will consist of different contributions corresponding to different locations on this surface. Each of these contributions will have its own amplitude and its own phase. And if we want to calculate the intensity, of course, we have to add all these electric field parts, square them. So let's put that in a little bit more mathematical form. So we can write all these electric field components, these small electric field components, in complex notation. So the amplitude divided by exponential. Exponential with phase index, and we can draw this field as a factor in so-called complex way. The real part of this complex number is a times cosine of p. The imaginary part is a times sine of p. So draw a factor with length of 8 and 1. The angle of yeah.
What's the J?
The J.
The expression E1 equals A1 exponential.
Oh, that's the sorry, that is the complex number.
Yeah.
Yeah.
I figured.
Yeah. I think it's probably going to shift to the at some point in the presentation.
I.
So for the second part, we have a totally different amplitude and a totally different phase. So that is a new factor drawn in the plane. For contribution number 3, that's the same thing, etc., etc., etc. So you get a bunch of random factors in this plane, and this sum expressed over here basically, if you want to do that in the plane, basically means that you have to put all these factors head to tail in this comparison. So the end will be if you put all these factors head to tail, the result will be in the resulting factor here, which also has a certain length and also has a certain angle with the axis. So it means that we can describe this resulting field also in the form of magnitude times in complex exponential some resulting things. So adding all these individual parts with a new So if you would just sort of briefly go through through these steps, because that's it's more the result that is interesting than the whole derivation. So the resulting, so adding all these different field components, and I'm going to follow the notation of a book by Goodman, and he uses the symbol A for the electric field. So for a very few slides, A is going to be the electric field. Is the sum of all the small contributions, and just for convenience, it is normalized here by the square root. Out in terms of the complex exponentials. And you can, or if you like, you can split this again. The cosine to plus j times. Now, if we assume that the amplitudes and phase are independent of each other, which is a very reasonable assumption. And we also assume that the phases are different. We consider different conditions. And if we assume that the phases are normally distributed, then we can quickly jump to the following conclusion: the mean of the real and imaginary part of the total field is going to be 0. Basically, what that means is if you add a lot of these factors in the end, you will have a resulting factor pointing this way. But for the next set of factors, you will have a factor pointing that way, and if you calculate the average of that in the end, it will just be still have. So the mean will be 0. The variance will be 0. The variance of the total set of field. I have some proof of that, but I'm going to skip it. If you're interested, you can just start with the proof for yourself. So continue. I'm just going to continue here with this result. Okay. So now, if we have a lot of these small contributions of the electric field, keep adding them, then according to the central limit theorem, if you have enough random values, then the central limit tells you that the distribution is going to be normal, going to be close. So with that as an assumption, we check later on, but let's assume that the number of contributions goes to infinity, then the joint probability function for the real and imaginary part of the electric field is given by the normal distribution. What we understand by derived by reasoning. Which means that we can calculate the joint probability for amplitude and phase. So the real and imaginary part corresponds to the equivalent representations in amplitude and phase. So we just square root the real part squared, just the imaginary part squared. Phase is the density. Ratio like this, and you can calculate joint probability distribution from amplitude to phase from the joint probability distribution of the real imaginary part. And the way that we done this is by multiplying it with this is a standard trick in converting probability density function by multiplying it with the determinant of the so-called Jacobian matrix solution. This is just from the statistics textbook. There's nothing fancy going on here. This determinant is calculated by the first line matrix. So the matrix contains the partial derivatives. You calculate the determinant like this. It's the element which subtract the equation. In this case, it's not so complicated. The derivatives are easily calculated, and so the determinant is so what we can do now is we can substitute A here and get for the joint probability of amplitude in phase. So we started out with this normal distribution for the real and imaginary part based on the based on the central limit theorem, and so the amplitude and phase that converts into this expression, this distribution, a joint probability distribution. This is joint if you want to know the so-called marginal distributions, or amplitude only and phase only. You have to integrate over the other variables. So to find the distribution for amplitude, we have to take this expression and integrate it over all angles. If you want to find the probability density function for phase, for data, then we have to integrate over all possible amplitude. It's also something that is a little bit of calculus. You can do that. The result of the amplitude is this distribution here, so it's going to meterize by sigma, which is the probabilities of finding amplitude. The phase is uniformly distributed, that's constant, and that's good because that was one of the assumptions that we made. Slowly getting to the point of this. This distribution is called the Rayleigh distribution. It explains also why the telecom people call it Rayleigh fading. It's a Rayleigh distribution that is for the electric field, for the total electric field. But the electric field is not the thing that you can measure. What we measure is the intensity, which is the square of the electric field. So if we want to have the probability density function for density instead of for amplitude, we have to do one more coordinate transformation. We have to use the transformation that density is magnitude squared. So the same trick, we have to calculate partial derivative of the transformation, multiply it, and work it out. And the result is a distribution for the density given by the term in green, so-called exponential distribution. For the spectral intensity, the important property of this distribution is that we calculate contrast, the standard deviation over the mean, that is 1. That's the same as standard deviation and mean by the same. So if you take a spectral pattern, intensity, if you calculate the mean intensity in the spectral pattern, and you calculate the standard deviation of the intensity values in that pattern, the ratio is 1. This is the formula. This is the graph. If you plot the currents, intensity, log scale, exponential. Straight lines, as you can see here. Contrast. This spectral pattern. Okay, keep that in mind for 10 more minutes, and then we'll see what the use of all this is in measuring flow. Let's have a break for 10 minutes. Sure. All right.
Ja. Ja, maar helemaal niet tegen. Nou ja,
Ja.
Oh, oh, oké. Ja, dat mag wel. Nee, we hadden nog iets bij.
Ja. Nee, go ahead.
Ja.
Ja, sure.
We hadden een paar vragen zijn.
Ja.
We hebben een, ja, daar kan het bij. Want we hebben een heel groot gedeelte, dat hebben we al kunnen doen. Alleen is er een paar dingen waar we niet helemaal zeker over zijn. Die hebben we onderaan het document genoteerd. Dat is nog niet. There we go. Ja, there we go.
We hebben hier.
Nee, die.
Ja, deze.
Oké, bij.
Speaking of gedocumenteerd. Oh ja. Ja, misschien springen we nu een beetje in het diep hoor, maar we hebben specifieke
Ja.
vragen over het zijn.
Gaan we doen.
De eerste is bijvoorbeeld dat we niet. We konden eventjes niet meer terughalen waarom we aan mochten nemen dat Excel. Even kijken, ja, het springt een beetje per.
Zo, ik ben een beetje kip.
Oh, ik zeg het even. Foto maken?
Waarschijnlijk.
Ja, want we dachten eerst heel logisch te weten wat de eenheid was.
Ja.
We kwamen met cijfers te boven.
Ja, precies.
Maar dat we
Want-
verder gingen rekenen.
Ja, precies. Want we weten dat. Want uit de.
Kan de Simons ook wel even
Ja, pak hem maar
bijpakken?
heel even.
Ik wil druk zijn op de hoor, maar.
Die we weer invullen.
Nou ja, zo is het.
En dan ging het om B en dan had je naar B inzoeken. Vooral naar C.
We argumenteren wat de eenheid van die afstand is. Ja.
Maar er zijn twee dingen.
Ja, want in C wordt zeg maar aangegeven dat
Ja.
die dus
Dat ik ook nu in slide.
ja, micrometer. En als je hier dus in de tekst kijkt, zie je dat dit eigenlijk
Mhm.
overeenkomt met elkaar, dacht ik.
Ja, nee, dat
Die
uit
LC met,
Ja.
dus
hoe we het uitmaken.
alleen hier wordt die opgegeven, maar we moeten natuurlijk beredeneren wat
Ja.
het micrometer is.
Ja, nou ja, goed, je moet dan. Het heeft een beetje meer met de OCT zelf te maken. Diep kijken naar de OCT-systeem.
Ja, dat ook. Dan is het
Dat,
toch die
Ja?
slide van de
Het is toch dat?
Ja, want de range in die slide stond op 1 micrometer tot
10
10 micrometer in micrometers.
Ja, maar dit is
In
dan.
OCT.
Ja, maar dit is dan.
Maar dit,
Ja, maar voor een heel OCT-plaatje.
Sorry?
Dus je moet dan hier kijken, dit zou dan één lijn in een heel OCT-plaatje zijn.
ja,
We kijken wel wat dieper dan micrometers. Ik weet niet precies welke plaatje van jou zit.
van de slide.
Oké.
Dus deze.
Ja.
Dan de tweede. Hier. Geeft er dus aan dat we dus weer kijken binnen een range van 10 tot 1 millimeter binnen de pathologie.
Ja,
Dus
dat kan je wel eens vergelijken. Met OCT kan je wel eens vergelijken. Heb je dat. Kijk in Martijn zijn.
Even kijken, hij gaf. Ik denk, dit is.
Dit ken ik wel. Dat is dan. Bij Peter was niet bij de B. De vraag van fragmenteer op de eenheden van vraag op plaatje C zijn. We zitten nu te kijken, maar we hebben geen idee hoe we dat moeten fragmenteren. Dus waar die al steeds begint.
Zo hierin. Oh ja, hij gaf volgens mij allemaal voorbeelden in.
Hier.
Even kijken. En zo. Dat is denk ik cardiologie. Ja, dat zijn allemaal OCT.
Ja, het zijn ja. Ja, kijk. Hier heb je al aangehaald.
Dit is een middenweg.
Ja.
En dat is het plaatje.
Dat is dus één plaatje. Ja, dit is dus de lengte, maar dit is dan een plaatje. Ja, dan heeft hij hier een diameter die van 10 mm ongeveer. Dan kan je dus ongeveer inschatten van, nou, hoe diep kijk je nou eigenlijk als dit 10 mm is.
Want hiermee geeft hij aan dat is dit.
Ja, dus dat rondje hier zeg maar is dan 10 mm. Dus dat is dan een systeem. Dit systeem kan ook helemaal 10 mm kijken, maar je ziet dat de diepteinformatie wel beperkt is tot een 3-4 mm. Dus dat is dan typisch de schaal van de QST.
Ja, alleen dan vond ik het heel raar. Dit. Millimeter. En dit dan.
Dat is micrometer. Dus,
ja, maar
dat
ja.
zou dan de vorm van liggen.
Ja, nee, ja, wel zeker.
Ja.
Ja, nee, we vonden het gewoon eventjes. Want we hadden eerst natuurlijk wel
Als het
gewoon
micrometer is.
hier dat.
Maar vraag me als het micrometer is, hoe komt het dan de coherence lengte van het systeem gelijk is een 10 micrometer? Want die bal,
Ja, oh ja,
de rode bal,
komt
die
uit op 125
ja,
units.
ongeveer 125 units.
Dus als dat 125 units is
Dan
van.
moet het 125 micrometer zijn.
Dat was raar,
Ja.
vonden wij.
Ja, dat is dan niet dan.
Ja, want ik kan inzoomen en dan.
Ja, ik geloof je
Maar het
wel.
is zeg maar. Ja, we hebben natuurlijk een beetje het gevoel. Als
Ja.
het 57 is, dan zit hier 625.
Ja, dan zeg ik dat heel klein moet zijn. Maar goed, van net zoals in C staat, je moet gewoon rekenen met die 10.
Ja, met deze 10
Ja.
micro.
Dat is een 10 is een redelijk normale
Waarde voor coherence.
Ja,
Oké.
10, 15.
Oké, en dan de volgende vraag.
Ja, volgende vraag.
Ja, we hadden ook nog. Even kijken.
Oké, ja.
Oh ja, dat is die van G.
Ja,
Over
oké.
die
Daarbij moet je
voxels.
de interferentiepatroon nee, niet het interferentiepatroon, maar de scattering
Oké.
terugkaast van één voxel. De dimensies van die voxel worden bepaald aan de hand van de resoluties
Ja.
van in de diepte en in de omtrek van het OCT-systeem. Nu hebben wij een vraag. Hoe
Over.
bepalen wij die laterale resolutie? Die axiale resolutie is de coherence lengte. Ja.
Ja, en
Laterale resolutie, daar hebben wij twee manieren.
we hebben een formule gevonden daarvoor.
Ja, we hebben op twee manieren
Ja,
denken we dat ze
dat
kunnen
kan wel
bepalen.
zien.
Of aan de hand van de numerical aperture, of aan de hand van de beamwidth. Ja. We hebben geen idee hoe. Dat is het probleem. Bij die Jeetje. Met dan is deze afstand tot het midden. En de rand van de
Die had ik al ja.
dat is wel nodig dat hier een bepaalde reden. Dat is de coherentielengte. De coherentielengte is de segmentatie in de diepte. Dat is die ook. Dus dat is die ZR.
Nee, dat is die LC.
Nee, je hebt twee dimensies in de diepte. Je hebt ZR, dat is zeg maar het stuk waarover. Ja, precies. Dat is zeg maar het stuk waarover deze bundel smal is. Ja, ja. En op zo smal heeft het dan een diameter van
Ja.
Ja, precies.
Ja, dat
Want-
staat ook in de.
Dat is dan ook van de deeltjes die meedoen in een bepaalde flexie, die kan, dat zijn alle deeltjes die op afstand tot en met de coherentielengte van je referentiewas.
Ja, dat is dat verschil.
Dus als je zegt van ik krijg dit van fase 4,
Ja.
dan betekent dat ik dan alleen in dit stukje, als
Ja.
Dat is net een detector.
Ja, precies. Dus al de deeltjes die in deze ruimte zitten, die nemen allemaal mee. Die geven het signaal van, van de ene box. Ja, precies. Oké, dat snap ik wel goed. Want wat ik in de eerste instantie had gedaan, is had ik die inderdaad deze formule gebruikt om de oppervlakte van die box te berekenen. Bij de tweede formule dacht ik misschien van, door met de NA kun je terugrekenen naar resolutie, kun je aan de hand daarvan de oppervlakte berekenen. Maar dat is dus ook niet.
Ja, zo niet van.
Ja, en
Nee,
dan
maar je kan
ook op andere waarden uit.
Ja.
Dus oké, dat is mooi, want dat had ik in eerste instantie goed gedaan.
Derde.
Het laatste was.
Zit hierin.
Oh ja, het laatste was. Kijk, hier. Dat was een vraag met het allerlaatste. Dan moet je het dan moet je integreren over een bepaald interval.
Die grenzen.
Ja, precies. Het stuk wat op de lens valt, om te bepalen hoeveel licht er wordt gescatterd. Ja. We vragen ons af, wat zijn die...
Boven- en ondergrens, want we
Ja,
dachten.
precies. Wat ik me voorstel is dat, kijk, als het hier, lichtstelsel zit hier zit de sample. En er komen spiegels doorheen, maar dit lens zit in het pad van de straal. En dus dan meet hij de scattering aan de hand van de straal. Maar als je dat doet, als je dus op nulpunt als referentie neemt, dan krijg je omdat een functie, de cosinusfunctie symmetrisch is rond de 0, krijg je een waarde van 0 terug.
Welke cosinus bedoel je?
Hier, deze. Kijk, dit moet even weg. Die plus half had ik gedaan om even iets te krijgen. Maar als je zegt, kijk, is dat die
Als je die halve die dus weglaat.
waar is die vermoeden?
Hieronder.
Ja, maar ik had die. Oh, shit. Ja,
Rustig
nee,
aan.
maar ik had die formule zonder ingevulde waarden had ik opgeschreven.
Nee, je hebt hem niet in de proefstuk geschreven. Met je op die. Ja, dat je ook. Dat is een maand.
Oké, hier. Ja, deze formule.
principe kan je gewoon zeggen zonder die halve.
Ja, precies. Als je vanaf min b tot beta tot beta doet, dan krijg je een functie die symmetrisch is rond het nulpunt. En omdat het resulterende functie een cosinusfunctie is, die symmetrisch is rond het nulpunt, krijg je een waarde van 0 terug. Als je over dat interval.
Ja, maar wat je doet is je moet in tijd over twee moeten die mensen die pakt een koon, dus precies. Deze boek.
Dat heb ik ook gedaan. Alleen de functie. Weet dat? Oké. Oké. Oh. Ja. Precies. Kijk, want ja, precies. Ja, mag je nog eens even kijken? Maar er zou even verteld uit. Maar nu staat je fout niet maken. Want ja, precies. Nu is het gewoon niet maken. Dat is wel tekenen 2 keer. Met de één, ik gebruik als het 2 keer in. Met de ene omdraai, de van de andere. Nee, dat was niet dit voorbeeld, dat was die voorbeeld.
Oh ja, dat is eigenlijk een cijfer.
Dus net betalen we half 4, en dat is wat ik nu erin doe. Maar dat hoeft maar 1 keer deze week te doen, want het gaat dan heel rond de TV, zorg dat het helemaal rond gaat. Ja,
Dan heb je daar een.
Ja. Meer. Hartelijk bedankt.
Graag gedaan weer. Hello, guys. Let's continue. So the big takeaway of what we did before the break was that if you start from the fundamentals and then try to calculate what the intensity distribution of the speckle pattern is, if that the distribution of intensity follows an exponential distribution. Result number 1. Result number 2 is that if you calculate the contrast between such a speckle pattern, then for an exponential distribution of 1, so the ratio of the standard deviation over the mean density. And then so now we're going to see, of course, how we can relate this to flow and to movement. So first of all, let's take a number of these speckle patterns. We have a number of pictures of such a speckle pattern, and that we should look at this. So if you would average before we take the picture, so we would overlap using different laser quantities, for example, then nothing would really happen because we would just get more parts of the electric field coming to the detector, which would just go into the same speckle pattern. So if you would do this addition based on the electric field, then we would still get a new speckle pattern with an exponential distribution with a contrast of 1. And if you would take the pictures of the speckle pattern and we would average these, so we would do the averaging on the intensity, then the contrast reduces. Contrast reduces with a factor square root of n, understand the number of averages that we take. So by averaging, contrast diminishes. This is actually the most it's a common form of speckle reduction. It's also the reason why we don't see speckle here from day to day, because we're averaging with our eyes a lot of speckle patterns of all different colors. If you would be able to look at just one color only, one specific color, then we would see a speckle pattern. But because we see all the colors simultaneously, everything, this contrast reduces, so it's really large in that case, and we don't see any fluctuations. So everything reduces the speckle contrast. That's point number one. If things move, contrast is reduced. If you look at take a photograph of the fast moving object, I have no idea what it was in this case, but you can see that the contrast is completely gone. So if things move, contrast is reduced. That same thing also holds if the speckle pattern moves. If you have a speckle pattern that moves within the capture time of your camera, then the contrast will be reduced. So an ideal speckle pattern, snapshot speckle pattern, will have contrast at 1. Some averaging happening, then this contrast value will drop below 1. And that averaging can be due to movement, like I said, so there's flow within your image, or moving of the laser pointer. If there is moving of the laser pointer on the wall, then you will see the speckle pattern. It can also be due to the measurement system. If the resolution of your camera is really poor, then it will capture multiple speckles simultaneously. If the integration time is really long, then speckle changes moves, speckle pattern moves within the integration time, then the contrast was. So first is the spatial pattern. If the imaging is in such a way that the average number of speckles, so let's say we calculate the total area of speckles and divide it by the area of one speckle, so let's say it's 5. On 1 pixel we have 5 speckles. So 1 pixel of the camera we have actually 5 speckles. That means that the contrast is reduced. So camera with large pixels. But at this point, we're more interested in the temporal averaging. What happens? Electric fields fluctuate in time due to flow. So there's some. I'm shining this laser pointer on a piece of tissue now. I get a speckle pattern. If there was no flow at all, the speckle pattern would be stationary. It would not change. Ideally, the contrast in that speckle pattern would be 1, but now this flow because it's not moving, so this speckle pattern fluctuates in time. One step earlier, the electric field at the detector that also fluctuates in time. That is something that we do not measure directly. So let's say it is some kind of random fluctuation with a random place, and it was really messy like this. This we cannot measure. What we can measure is the so-called correlation function. So we take the electric field, still a mathematical exercise, which we don't have to do. We take the electric field and multiply it with a time-shifted version of itself. Here the electric field is P, this is and we multiply it with a time-shifted version of itself, and then calculate. So what will happen is that if tau is this lag parameter is 0, then we are essentially multiplying the electric field by itself. So we will get the area under this graph, and we'll have some term. If we multiply with the shifted version that is shifted quite a bit away, then we're multiplying 2 random signals, and the result will be something else. And what you'll see is that if you make the shift larger and larger and larger, is 0. We're basically just squaring the signal with the distance between the original signal and its shifted version becomes larger, then eventually this correlation value will fall. So that's basically the correlation telling you that the signal will at short values of tau, the shifted version really resembles the original sample. Tau gets bigger, the shift gets bigger than multiplying with something that is not really like this. Yeah.
Sorry, I couldn't really hear what you said about if the shift version becomes larger, how would the graph?
So you take a portion here. And then and here you have the same, you have a portion that is from here, so farther away.
Yeah.
So if these two portions are really close, they're still more or less the same. So this product adds up to a given to a given value. But if the distance is larger and you have some random signal here, some random signal here, and then it's very likely that the product of these two random signals is lower.
Okay, yeah.
So that's what you get. So when you increase the style, that means that this part, the shifted part, gets farther and farther away. And then this product, this correlation, that's what that's. Okay, now this correlation, this is again a function, and again a function is not so convenient to work with. So this one is characterized by a characteristic time or a decorrelation time, which you will formally integrate like this. You will take this function and you will integrate it from 0 to infinity. So basically you're calculating the area with this curve once again. If you do it that way, you get this characteristic time. For a correlation function that is shaped like this, which is an exponentially shaped, this is just the time constant of this. If this is a very steep function, the correlation time will be very short. If it's a function that really slowly decays into the correlation, it will be much longer. We can normalize this correlation function. So, and this is what we have. We have the field multiplied with the second version, and then we normalize it on the value of this. So we normalize it on starting here. So now we have 1. And still, this correlation time calculated the same way. Why we do this normalization? Well, simply because now you will get something that only depends on phase differences and not on amplitude. So if you have an electric field that is written here in complex notation as an amplitude times phase term, then the time shifted version will be the same amplitude plus time shifted phase. You calculate correlation function, and it would be amplitude squared times this two phasors. Tau is yeah, okay, yeah, so the T's will count to the one you have time difference here, and you should then normalize it. The term within brackets is speaking, so it's only a function. Now this phase difference, so this is the phase difference then for at a certain time, measured at a certain time, and then at a certain time tau later. There is a phase difference because the particle moves. So the particle gets a new position, so there is a new phase arriving at the meeting. You can calculate it, so basically we'll do the same trick all over and over again. We take a particle at a certain position that is illuminated with the electric field. And we're interested in the electric field somewhere out there. That's in detecting. Now, this particle moves, so if T is 0, the particle is here. If T is tau, the particle is here. The new field, so it's illuminated again. Same field, new field will be at the effect. Question is what's the phase difference? What is the phase difference? But this situation is of course the same as something that we already seen before when we calculated pair correlation functions and structure factors. It is just the phase difference between these two particles. The only difference is now that first the particles were there simultaneously. Now we calculate these particles. So that the calculation runs along the same lines, which means that I'm not going to repeat it. But I'm going to show you briefly how the result actually. Here we go. One back. So you can calculate the phase difference between these particle here and the time tau later than the particles here. It's given by the distance it travels in the time t. The tau times 2 times k, is the wave number to pi over lambda, and geometrical term is cosine between the direction of observation and the direction of particles. So if you write this phase difference as a frequency times time, so then delta r simply is phase to phase, the speed times tau, velocity times time. Then we can express it as a frequency, as a frequency shift delta f, so the number of times data. And this is just the Doppler shift. This is just the Doppler frequency of light that passes against the moving particle. This is the result. We remember change in frequency is proportional to the cost of the angle between the angle between observation and the direction of the force. So in a measurement that would tell you something like this, you would have a block velocity that has a certain direction in the angles. You would shine light in the one angle in one direction and measure that's out in the other direction, and you look at the change in frequency between these two wave factors because of the walking there staat. That is a bit you can do the same thing for sound waves and ambulances. So how does that then work in practice? You'll put up a photo diode here, laser light shining in here, and you measure the light in the diode. That will give you this fluctuating signal. This is a contribution of light that is scattered from stationary structures and from moving red blood cells. You get this kind of appearance pattern with light that is scattered by moving cells as a frequency signal. We measure this signal for some time, and then do a frequency analysis. So you take the Fourier transform, then calculate the power spectrum, and the power spectrum you calculate the mean frequency. So there's a lot of math going in there. It has been shown, and we'll constantly find it, that if you calculate this frequency, it's proportional to the root mean square velocity so that's how this measurement works. You measure the fluctuation in time, take the Fourier transform in the spectrum, you calculate the average value of the spectrum, which is proportional to these values. It's also proportional to the concentration of red blood cells, so the number of red blood cells, provided, and that's where it gets taken then, provided that the concentration is not too high. So with the total power that you receive, the detector is also proportional to the concentration. If you have more blood cells, you will get more light scattering effects. So total power is also. Final analysis then is you calculate the spectrum, you calculate the first moment of the spectrum, the average of the spectrum, which is proportional to velocity and concentration. And you divide it by the power spectrum itself, which is the concentration, and you get something that is proportional to the velocity. See, with unsatisfactory thing going on here, because start out with something that looks really physically with the speckle pattern level, and we do a lot of calculations that look formally correct. And in the end, you get a result like this. So we have, we can do a measurement and we get a velocity that is proportional to what we measure. So it's qualitative, it's not quantitative. It's not possible to calculate the absolute velocity. But nevertheless, it's not difficult to do. The only thing you need is a laser and a detector and measure for some time and a computer to calculate the Fourier transform. So what people have done is build these devices, and if you then incorporate a little scanner that scans the laser beam across the tissue, then you can make maps of blood flow velocity. What you see here is images of two hands. In the resting case, you see some red corresponds to higher velocity and blue corresponds to lower velocity. What you see here is that there is an increased blood perfusion, blood flow in the fingernail region. So that's well known. The nail bed is really well perfused. So there you see that. So what they did then in going from A to C to D is they added tiger balsam to the hand, balm, tiger balm, needle thumb, something that they have used if you sport event that increases the perfusion, and indeed you can see. And you can see that the perfusion is increased. Increased in this region. But still, there is no quantitative scale because it is qualitative. The other method that also is based on speckle is laser speckle contrast imaging. So to see what's going on there, we briefly take a few steps back to this correlation function. It's normalized so that it only contains phase differences. We can summarize this decorrelation time. I've got this decorrelation function in terms of the phase term in phase term here in this expression is given by Q and delta on t, so that's the distance that the particle moves in time t, such as that distance. This is actually what we did. There's buffers, and we did that, so skip this one. So we're going to move now to this to laser speckle imaging. There's a couple of ways of doing that with more or less the principle is essentially you still have a laser that illuminates tissue, and you have some kind of detector, usually a camera, but it can also be a point detector that captures the scatter line. What we want to do again is first measure the fluctuation of the intensity, and from analysis of that fluctuation, we try to get like this. This analysis of fluctuation can be done spatially, so you can take a region on your camera and calculate, for example, the mean and standard deviation of fluctuation in that area of the camera. You could also take multiple frames of the camera and calculate the mean and the standard deviation over the same pixel within at different time points, or you can have some hybrid where you measure both in space and in time. That's all possible, and it's possible people do that. So this is a list of laser speckle techniques that use various ways of averaging the spatial domain, or the temporal spatial domain, or spatial temporal, both different techniques. And of course, because you can, they all give that technique different abbreviation. But essentially, they all do the same things. They measure fluctuation, calculate the mean, standard deviation, every time. So these are results that you can get from that. So this is averaging purely in the spatial domain. See that the resolution gets a little bit poor. This is averaging purely in the temporal domain, so the resolution remains very high. It takes longer to do this measurement. This is then the trade-off, where we do a little bit of averaging in the spatial domain and a little bit of averaging in the temporal domain. So compromise and as comparison with basic measures. So the same kind of data is obtained. You'll also notice that there are bars here that represent how much perfusion there is, how much flow there is, and you will also notice that the units on these bars are vastly different. So again, here we have no quantification. But we can try to make this a little bit more quantitative. So let's first see what happens when we integrate such a fluctuating signal over the detector response time. So the detector has a certain time during which it's measuring. In that time interval, there is some fluctuation. So what is then output of the detector? You can write that as follows. The signal is fluctuating with the table here, and the detector is on for a certain time. Measures, and then goes off, and then goes back straight. So for each time point, you can describe that process as a rectangle function that is on for some time. So you multiply the fluctuating signal with this rectangle function, then add everything underneath the product up, and that is then the signal that you get. So this is how you would mathematically treat temporal averaging of the detectors. If you do this averaging, then the average intensity doesn't change. Same with the standard deviation. Standard deviation builds fluctuations. If this is fluctuating really fast, then due to this averaging over a certain response, the fluctuations will dampen out a little bit. So standard deviation will change. So that means that the step of contrast, the integrated signal will be less than 1. Okay. So due to this time averaging and time integration, contrast drops. If you have you can formally write that. So your measurement is the electric field temporal autocorrelation function. That was that contains more information about the fluctuations. There is an integration window during which the detector measures that signal or averages that signal. There can be some spatial averaging because your detector or your camera has pixels that are too big, for example, so that's like beta. This is the integration time. So this is the contrast that you will measure in a real measurement. So contrast would be 1 if you did not have the spatial and the temporal averaging, but now you have. So due to time t, integration time t, and due to beta, the contrast will be both. So, if you would like to do something with this formula, so this is something you can write out and then take for granted. Because if you would like to do something with this formula, that means that we need some form for G1, some expression for G1, in order to put them in. So the question is: are there simple forms? Are there simple forms of G1 that we can use so that we can get simple models? If we get simple models, then we can use it in online real-time measurement. So let's see if we have scattering from a group of particles. Let's start with the ideal G1 that averages over these many particles the distances, phases that result through the distances that they travel with time t. So there. And furthermore, now assume that each of these particles moves with its own unique velocity P, yeah, which is for J, and the same, but it can be different, but it's method. So G1 would average over all these velocities. Now you can you can then use again a formal way of mathematically doing it. I've written it down here because otherwise start messing up how you do that. But basically, if you have a distribution of velocities, then you would multiply this expression with a distribution of velocities and then calculate that. Now, what happens in tissue is that let's say you have a vessel somewhere deep inside the tissue. The blood is flowing through the vessel, so that has a certain direction. But the light that interacts with that blood has come from the top, has interacted with all kinds of static tissue structures before it reaches the vessel. So the photons that actually bounce off the blood cell have their directions already randomized. So you can take that into account. This direction between the light and the direction between the photons is isotropic. So that means that you can simply assume a normal distribution for the blood flow velocities and plug that into the equation for G1, then you end up with a simple expression. That has only the mean velocity. There's one step towards it. And one step towards a somewhat simpler method. You can make it even simpler. So, if you look here, it has the mean velocity. We can write the mean velocity as the mean square displacement. The velocity squared as the mean squared displacement here. And you can identify two forms of motion. There's Brownian motion, so that blood cells move in random directions. Then the mean square displacement is given by a Brownian diffusion coefficient, like this expression. Or if the flow is really directed, then it is simply given by the mean directional velocity squared directional velocity. So these two variants can be plugged into the general notation. So here are the two simple expressions for G1 that are used to relate the decorrelation of the swap pattern with velocity. There's a Brownian motion with the information about the diffusion of the blood cells in the case of flow having a certain velocity with that information. Now, if you assume that the measurement is done in back reflection, that means that the scattering factor Q just becomes K over K, then we end up with an expression for G1 that is a simple exponential decay, K over decorrelation time. 1 over decorrelation time is proportional to the diffusion coefficient, is proportional to the root square velocity. The same thing happens when you use the Gaussian model, Gaussian for the order flow. You can plug in the expression for mean velocity. You will get G1 form that is T over decorrelation time squared. But the result is the same. The decorrelation time, the inverse of the decorrelation time, proportional to the root square velocity. So this is the direct link, finally, between velocity, root square velocity, inside the sample, and the decorrelation time of the spectral pattern, which you can measure. So this is now the approach that all these techniques take. We try to measure the decorrelation time of the spectrum, and then use that to estimate the velocity. And again, for Brownian motion, is this expression for ordered flow of Gaussian flow. This expression with the assumption always that the decorrelation time is the first. Okay. Let's have a break. And I will briefly stop the presentation here because I want to throw out a couple of slides that are really too much. So if you can take 15 minutes, then I have a little bit of time of 15. Okay, guys, let's move on.
Heb je gewoon van.
Yeah. The result of the derivations before here was that we could measure speckle contrast using a detector that has an integration time t, and that maybe averages spatially according to a factor beta. So that means that we can formally calculate the contrast that we will measure as a function of this decorrelation function. The decorrelation function can come in two shapes. Two exponential shapes. One is a single exponential, corresponds to Brownian motion. The other one is a Gaussian form that corresponds to ordered flow or Gaussian flow. Both of these have the time constant, the characteristic time constant type A. The assumption any of these derivations is that this inverse of this time constant is inversely proportional to the buffer. So in this case, by the root, we have a link between velocity and contrast. And hopefully then the idea is that if we can measure contrast, that we can trace all the way back and measure velocity. The situation is a little bit more complicated than that, because not only will we see speckle from moving structures, but also from static structures, and that needs to be taken into account. So people have done that. So in the end, that leads to expressions for the contrast, filling these G1 expressions into that integral, and then also accounting for fraction rho of static. Only fraction rho is moving and 1 minus rho is static. The expressions become a little bit complicated. So this is contrast. The beta is in there. The fraction rho is in there. The time constant that we're after is in there. Of course, the integration time, the detector in there, and some noises. But again, the assumption remains that, however complicated these expressions are, that the decorrelation time is proportional to the velocity. Of course, if we have this many unknown parameters, if we don't know data, if we don't know rho, if we don't know noise, then we need multiple measurements to solve for the decorrelation time. The easiest way to do that is by using the decorrelation time, the exposure time. The exposure time on the camera can be easily controlled. So what we will do is measure values of the contrast with multiple values of the exposure time. Then hopefully be able to extract all these values, and then of course see most important. So how that will look if you take a speckle image and if you increase the exposure time, then obviously the contrast will decrease. So you will get from your ideal contrast 1 to and now deliberately, because we increase the exposure time, the pictures that have less and less. Of course, apply that for also do that in the window of certain size, so this is type space pixels. It's the same trend. Contrast decreases, increase the exposure. So the magic formula behind all these methods is that the exposure time or the correlation time is inversely proportional to velocity. So let's just define a proportionality factor alpha here. We can say something about alpha, then maybe we can say something about the feasibility of this approach, this measurements. Tau was the decorrelation time of the field autocorrelation function. So we calculated for different exposure times. With an alpha, this proportionality alpha is unfortunately is debated in literature quite a lot. Values have been reported in the range of 2 orders of magnitude. It's not so straightforward to use such a measurement. And to make things worse, there are system properties, multiple properties of the sample, considerations about multiple settings. They all end up in this spectrum house. So that basically explains why there is so much debate, and it also explains why all these measurements are still qualitative and not quantitative. If you don't know alpha, you can do a lot of work. You can do a lot of work to determine the decorrelation time. If you cannot translate it into velocity, it is still not very valuable. So what we have tried to do with the students of ours a couple of years ago is to refine that magic formula a little bit and split it into 2 components. One component is still a factor alpha. The factor alpha is valid now for a single interaction of light with red blood cells. There is a new factor A of N that is a function of the number of interactions. So if the photons encounter multiple red blood cells, then that effect is incorporated into the factor A. So she did a lot of work on that, both theoretically and experimentally, and as a last part of today, I want to talk you through that work. And as you will see, a lot of things actually that we talked about today, but also in the earlier classes, we'll come back a little bit. So first of all, the proportionality constant alpha of a signal now is for single second events, so only one interaction per second, and it depends on the optical properties of the red blood cells and of the medium. Scaling factor for multiple scattering depends on the average number of dynamic scattering events in the pattern. So that means dynamic scattering in this case means that there's a scattering with a moving particle, with a dynamic particle. And it will depend on the optical properties again of but also on the geometry of the experiment. So that will become a little bit of a change. And then there is also, not in the formula, but also something that needs to be taken into account, of course, is that if you want to do an accurate measurement, the decorrelation time, you have to also account for this, other instrumentation factors for the fact that you have the proportion of the light that is scattered to non-moving scattering, and possibly other sources of decorrelation. If your patient is not lying still, then you get red blood cell movement just by moving of the patient, and not only because of that. So that's into account as well. So first of all, the theoretical work that she performed. This was the general expression for the decorrelation function as a function of Q that has the scattering angle in there, so the angle between the light, the observation light, and the velocity direction v. Yeah. And the first step is what she did is she incorporated the phase function. Phase function basically describing the distribution of scattering angles, the distributions of angles. It is here parameterized as the effect of Q, but it is related to angle, as you can see here. So integral of sine theta and theta. As we encountered in class, we can substitute that as we did in the Monte Carlo as an integration of the mu de mu, but you can make an additional substitution and write it as an integration of Q and Q. Nothing really fancy. Now, this phase function for a red blood cell is calculated using V theory, because the size of a red blood cell is about a bit larger than wavelength. And if you assume that it is spherical, you can use V theory. And also taking into account that the volume fraction of red blood cells in blood is really high, around 45%. That means that we have also included a structure factor. Search effect included in this case is the so perfusion. So all that information, mean theory, structure factors, all those in this expression here. That is the part of this. So if you calculated this one, so the velocity is still here, as you can see. You can also calculate the correlation time by this equation again. And if the shape of this phase function is approximately Gaussian, turns out to be the case, then this G single will have this form that is very much like this shape over here. So the decay of tau over tau c squared. So having that, so this theoretical exercise allows us to calculate the theoretical value for the alpha. I'll show you the value a little bit later. Up until now, this meant that photons only encounter one red blood cell. But if the vessel is bigger, or if there are multiple vessels, of course, then photons will encounter more than one red blood cell. And from each of these red blood cells, they will experience this shift, this faculty correlation. You can take that into account by assuming that all these interactions between red blood cells are independent of each other. So the probability of hitting the next red blood cell does not depend on whether it already has hit a red blood cell before. So in order to do that, if you assume that, then we are allowed to multiply the decorrelation functions for the single events. So if you have two events, you have one square. If you have three events, you're allowed to raise it to the third power. And if you have a distribution of the number of events to the n, then you have to sum over the distribution over all of the distribution of the number of events. So for that, again, you can make some assumption. Assumption is that it's normally distributed. That you and what so then the question is how can we get this distribution from the event? Now there, the pair correlation function comes handy. The pair correlation function is a function that describes the distances between particle pairs, but also you can calculate a lot of mechanical properties from the pair correlation function and also statistical properties from the sample itself. And one of these is the ratio of the variance in the mean of the number of particles in the substrate. It's calculated from the pair correlation function as follows. And if you use that same pair correlation function, then the expression becomes really simple. So the ratio of the variance of the number of particles or blood cells between the mean number of red blood cells in the volume is expressed only as a function of the volume function. And for blood, because the hematocrit blood is about 5%. So Annemarie went on, assumed that PFM was a normal distribution, and that the ratio of the mean and the variance of that normal distribution was determined by this expression, and then she did a bunch of Monte Carlo simulations to determine the mean number of specimens. Simulated, showing the simulation a little bit later on. And then from that mean, when you get from the Monte Carlo simulations, that could also be plugged in. Theoretical exercise. Continue. After that, we did experimental validation because we wanted to see if all this work was correct, and we used that same side stream dark field microscope device that you saw earlier. We modified it a little bit so that we have two modes of operation. One mode of operation is simply the conventional method. So having 4 green LEDs illuminated the tissue and then encapsulating the light and making this image. In this image, by tracing the red blood cells, we could calculate calculate red blood cell velocity. So that will be your ground truth, internal calibration. And then for speckle measurement, we changed it a little bit. We switched off the green LEDs and we coupled red laser light into the fibers. It's something basically we captured now the speckle image from the same calculation. So this is the two images that you will get. This is raw speckle frame, so you can see the calculations from the conventional microscopy image. This movie. Okay, so again, the analysis is based on this refined magic formula. G1 is calculated using the assumptions that the blood cell can be modeled as a mean scatter. We use the calculation function. The average flow velocity goes in there, so that's ultimately after that is calibrated, so we can find from the rest of the microscope. The result of the theoretical exercise, so the value for alpha is value of alpha is predicted at 0.38 plus or minus 3%. There's a little bit of variation because we don't know exactly what the size of the red blood cell is for the mean theory. We don't know exactly what the refractive index is in the mean theory, so we vary that a little bit so that we can get a little bit certainty. But this is then the theoretical value of alpha that we expect to find in an experiment. The probability distribution of the number of scattering events was determined using Monte Carlo simulations. As a normal distribution, so this is the geometry for the Monte Carlo simulation. So we have a vessel here where we simulated blood flow. This was illumination from one of these fibers in the instruments. The area 1 square millimeter was E square millimeter. This illuminated and captured all the reflected photons in this small area that was the detector field. So then by varying the simulation, so doing a lot of simulations, we vary the scattering coefficient of the medium first, and then extracted the average number of scattering events from the detected photons. So that turns out to be a nice linear relationship. The same thing can be done for different geometries. So we took a couple of systems that are used clinically, try to simulate that geometry in the Monte Carlo simulation, and then calculate as a function of vessel diameter what the average number of scattering events is. You can see it varies a little bit, but there is kind of a relation between the vessel diameter and the number of events. It means that if we can assess the vessel diameter, we can estimate more or less what the number of scattering events is. It's convenient results. So again, putting that all together, then jump straight to the result. Then this is the expected value, the theoretical result from the Monte Carlo simulation for the scaling factor. So the magic formula refined is that the decorrelation time will be proportional to a single scattering alpha, which using mean theory associated we estimated to be 0.38, and also dependent on a factor that depends on the number of scattering events. And that is shown here for two different values of the red blood cell volume fraction. First, we performed phantom experiments. So we took that same system that we tried to simulate in the Monte Carlo simulation. We built it now for real in the lab. So this is a block titanium dioxide particles in silicone. There's a small tube in there. We push particles through that flow particles. This is an OCT image to verify that we have this nice flow channel. Phase measurements of some. So what you see here is spectral contrast. So the contrast in the spectral image is a function of exposure. To these curves, we can fit now these complicated models that we saw earlier on that have beta parameters, that have rho parameters for the fixed fraction, and then in the end, you can calculate, you can estimate rho for long times, for long integration times, everything is very static. For very short integration times, you can estimate the beta parameter. So we get this data points, and we can fit and only we can fit only one parameter in the end. Now say at a certain imposed velocity in the experiment. So we now have tau c from the data and imposed velocity in the experiment. And this is the result. What you see here is flow velocity on this axis. One over the deformation time, and the other axis with different particle sizes and different volume fraction. And indeed, it shows that for all these experiments, we have indeed this inverse relation one over tau c is proportional to this. So that old assumption that indeed holds. The slope of this line is the factor alpha. So in here, it's also immediately clear that people in literature have reported different forms of alphas, because depending on which measure you do, you get a different alpha. Now our goal was to separate this alpha into two components, one theoretical component for a single event, and that's a scaling factor for more than one interaction event. So that is here. So the theoretical alpha, taking into account the multi simulations and taking into account the associated, was supposed to give this red line alpha as a function of the energy release of particles. You see that it works pretty well. The theory and the data corresponds pretty well with some of the large particles. If you have smaller particles, then our theory fails. We have no idea why. We haven't found out. Good thing. So in a different situation, this might we might have given up here, or we would have spent a lot of time trying to figure out why the theory does not work here. In this case, we didn't do that yet because the size of a red blood cell is about here. So red blood cells themselves fall in the regime where the theory seems to work pretty well. So we use that basically as a rationale to continue here. This is the same data the same measurement within a different graph. So here we have the theoretical alphas, and here are the alphas that we obtained from the experiment. And again, for a subset of data, it works fine. For smaller particles, it does not work so well. And again, red blood cells typically live here in this region. So we decided to carry on and did two experiments with actual blood. One is the chicken blood. So the chicken chorioallantoid membrane model is basically a fertilized egg in which an embryo is developing. And what you can do with such an egg is you can take off the cap, so you get a clear view of the developing embryo, and you can measure its vasculature. So in this case, that was done at day one. Everything was fixed, and everything was fixed so that we had as less as possible appearance. And we did the model calculations, predictions specifically based on the data that we can expect for chicken blood. The red blood cell of chicken are slightly larger than these humans, 7 micron, The blood volume fraction is typically much lower, 22%. The refractive index we did not know, so we set that the same as for human blood. And we estimated from this scattering coefficient of 95 millimeter and scattering anisotropy, so the full correction of 0.99. The other experiment is in the human microcirculation sublingual, and it's under the tongue. Circulation there is pretty accessible, of course, you can imagine it. And it's also superficial. You can easily do that. So that is with that same device that we. So these are then the properties for human blood cells. The diameter is 6 micron. Volume fraction under the tongue is a little bit less than the whole blood, so 30% is estimated. Refractive indices for the meat theory, and that gave scattering coefficient 2 per millimeter and scattering loss. All these data go in the model prediction, and then with the side stream dark field mode of the experiment, we can do the validation. So this is how these measurements look. This is for the chicken model. Here you see the side stream dark field measurement. So the frame from that movie that shows the blood cells here with dark spots. Uses green light, so the blood cells appear as dark spots. And by tracing them from frame to frame in the movie, we can calculate the velocities in the different vessels. Now, then from the speckle decorrelation image, this is one of the integration times. We take this contrast image and look for decorrelation times, then construct a decorrelation map. So here you can see 1 over the decorrelation time on this color scale. So here you can clearly see that there is also already some kind of contrast for the vessels, so the flow is going on. And then finally, what we did is from these images, we created a mask, so where the vessels are or not, and we overlaid that mask of the decorrelation method to finally translate that into a flow velocity. So what you can see here is that if you compare the colors, this is in micrometers per millisecond, and the flow velocity is there also in micrometers per millisecond. Is that the ballpark range of flows? So here, for example, we have 0.4 micrometer per millisecond that corresponds to this vessel, which is indeed so it is more or less is in the right range of flow velocities. Same. This is the microcirculation under the tongue, so the same thing. This is the control image, control movie, then frame with the flow velocities. They're slightly higher than the chicken wheel. Again, this is one frame of one integration time of spectral images. By doing that on multiple decorrelation times, you can construct a decorrelation map. So this is 1 over the decorrelation time. Combining that with the vessel map obtained from the side stream dark field, we get this segmentation, and again, you can see that we have lower blood flow velocities. See there, in this small vessel, the flow velocities are slightly high. So we did that. We repeated that experiment, of course, for quite some vessels to obtain some data. And what we saw is that if we plot the raw data, so simply take the decorrelation time and plot it versus flow velocity, we get for both the chick embryo and the human, the result of the correlation is not that high. You rescale it. Yeah. So if we plot that, we expect that the inverse of the decorrelation time is proportional to the flow velocity. So you would expect something like a straight line in this in this graph, both for the chicken embryo experiments and for the bug experiments. As you can see, if you simply plot the correlation time, then the result is not so great. So the correlation here is only 0.11, here 0.48. So that is not so good. But if you then rescale it using the theory for the multiple scattering events, then you get a much better correlations, 74% and 87% in case of chicken and embryo, and then the slope. So the alpha factor that corresponds to that is for the chick is 0.2 plus minus 0.7, whereas the theoretical, the model prediction was 0.24. So that's really good. And then year two, if you do the rescaling for the multiple scattering, then the experimental value for the slope is 0.39, whereas the model predicted, or the model based on meteor observing predicted. So that shows that. It shows that the model is okay, but that in the end that you do need to really do that, take into account that live encounters that lots of model has. So finally, taking all these steps and translating the decorrelation time that is obtained from the speckle measurement to a velocity. We can now here plot the velocity from speckle, obtained from speckle, from all these calculations, versus our ground truth velocity obtained from the side street dark field measurements. And then you see that both for the chick embryo and for the human blood, which is ideally the points which follow the unity line, of course. But this is then what we get next. So basically what the thing is that we are one step closer in making this whole method quantitative. So quantitative, so this takes a lot of those take a lot of steps. Okay, so the conclusion. The ultimate goal is to quantify blood flow velocity. And one of the methods that has been really popular is doing that by contrast imaging, because the measurement itself is really easy. And also because what people do is assumed that there is an inverse relation between the correlation time and velocity. We have shown that it is actually true, that this assumption is valid. What people do usually is take a single proportionality constant, and because it has multiple factors, this can vary tremendously along literature, which means that you cannot compare the results from one machine to the other, for example, because each uses its own proportionality. So what we propose is to split this proportionality factor into two terms. One term we modeled based on single scatter Lie theory, based on pair correlation coefficients and structure factors with discrete on media. That gave us a theoretical value of alpha single, and we estimated the contribution of AN using Monte Carlo simulations. That way we could predict what this factor will be in different dimensions. Maybe these experiments on chick blood and on human blood on the tongue to validate this approach. And we saw that it seems to work fine for the larger particles as when blood cells are, which is a happy coincidence because the model fails for small particles. Of course, there is no reason, at least in our derivation, there is no reason why it should fail for small particles. So that is still something that needs to be addressed. Also, what is less elegant a little bit is that it relies on Monte Carlo simulations to determine the average number of scattering events. Would be nicer if you would have some kind of complete theory that would also predict that. And it relies on along the way on assuming that waveforms are nearly Gaussian. So that could be this assumption could be one of the reasons. But we don't know. That is still work in progress. Where that work is. Okay, last slide. So for the flow and perfusion, we looked at the three techniques: microscopy, that was near perfect. We had limited direct flow velocity, direct images of the micro circulation. So where it works, this is the way to go, the way to do it. If you want to measure a little bit deeper, or you want to measure faster flow velocity, then you have to rely on the speckle-based, you can rely on the speckle-based techniques, laser Doppler function, speckle context imaging. And as I've tried to explain to you, there is quite some challenges with quantifying these results. And yes, the work we did a couple of years ago was aimed at least trying to quantify these speckle context imaging. Well, that's it. Thank you again.
I'm not good.